Okay, Tom, I want to thank you for passing out the magnets for the lab that'll help us kind of explain what we've talked about here so far with the different forces, and today, as we've discussed, with the strong nuclear force. Now, David asked a question earlier that I said we'd get back to, and that question was if electromagnetism, that force, states that like repels each other, right? And that opposites attract. Like these magnets, if we put like for like, they don't want to go together. They want to stay separate. But if we were to spin it, then they want to stick together. So like for like is repelling, right? And opposites attract. And we know that within the nucleus, which is held together by the strong force, as we discussed, that all of those protons are positively charged. So they're all like for like, but yet we know that they're all packed in there and they're close to each other. So he asked, why doesn't the nucleus and those protons separate from each other? And I said we were going to get to it, and the easiest way to demonstrate that is with these magnets. So to understand that, we need to go through two rules. One we've just discussed. Rule number one, using the law of electromagnetism, is that like repels and opposites attract. We showed how that works with these magnets. So if everybody would go ahead and find on your magnets which side is the positive and which side is the negative. Now on mine, the two shiny metal sides are opposite from each other, and the two shiny on the other side are both the same. So you would have to put them like that. In essence, shiny side to not shiny side, right? These are same, and these are same, those are opposite. Did everyone find that? Great. So now we know which ones are positive, which ones are negative. I would like you to go ahead and, using your dry erase marker, I want you to mark on these which one are like for like. You can use letters or you can use positive and negative. You actually don't know which one is positive and negative, but go ahead and give some symbol to be, this might be positive and this might be positive, and this might be negative and this might be negative, so that you know which side are which. Go ahead and take 2 minutes and let's go ahead and do that. I would of course wait about 2 minutes. Okay, so we have our sides. We know which ones are like and which ones are opposite. We know rule number one is that opposites attract. Everyone go ahead and find the opposite. So you should have a plus and a minus and stick those together. And what do you got? All right, did everybody stick together? Of course it did. What happens if we take it the other way and we add two that are both the same charges, so both negatives or both positives? Go ahead and everyone give that a try. Can you get it together? You could probably force it, but you can feel that there is a repulsion there, that they don't want to go together, right? This is about as close as I can get mine before it gets really, really difficult. Everyone is about the same? Great. So that is our first rule. Electromagnetic forces are like repels, opposites attract. We've seen that on these magnets. Now this is really the best way that we can look at subatomic particles and their charges. They're so small we can't hold them together and do it. So this gives us an idea. Let's go with rule number two, and that is that the strong force is a contact force. It must be touching to overcome other forces such as electromagnetism. So why doesn't the protons, all positively charged in the nucleus, repel each other? Well, because there's a strong force enacted upon it. However, the rule is that the strong force must be a contact force. It must be touching. Okay? So you'll notice on all of your magnets on the very bottom, there are Velcro pieces. Okay? This is much like the strong force. So here we have our two likes. Mine's negative and negative. And of course, they want to repel each other. But if I can make those two plates touch with the Velcro, which is an example of our strong force, we see that they'll stick together. Okay? You can see for yourself if everyone takes this and you stick it just right and you get that Velcro together, you can cause there to be a gap. Oh, mine just came apart. But your Velcro will actually, or your magnets will actually repel. There we go. But the Velcro will keep them together. So you can see there's a gap in there. Right? Everyone here's a gap, and you can feel that it's pushing against each other, but you can keep that contact there by putting the Velcro together, and the Velcro is stronger than the electromagnetism, and therefore, if it is in contact, it overcomes the weaker power of electromagnetism. However, remember that the rule is that strong force must be in contact. If I take these two pieces of Velcro on my magnets and I just put them near each other, they don't overcome that weaker force. They don't attract each other until they are in contact with each other. At the time of contact, that is when they will overcome the weak nuclear force. So if they are not touching, then we know that the only force enacting on those two subatomic particles are the electromagnetic forces. If two like particles are touching and they are staying together, we know that a strong nuclear force is being enacted. So I'd like everybody to take your magnets in your hand, and I want you to bring the two Velcro pieces, which are on like charges, negative and negative, and bring it close to each other. Is anybody's magnets being attracted to each other? No, of course not, right? You can actually still feel that repulsion. Now I want everyone to push their Velcro pieces together and then let go. Does everyone's Velcro overcome that electromagnet? Is everyone staying together like this? Of course, because that Velcro is in contact with each other. So we can see that the strong force is a contact force. It has a very short distance. It must be in contact. Whereas electromagnetism has a longer range and can enact with each other just by being in proximity. So those are our two rules, right? Electromagnetism is that opposites attract like repels, and that they can be enacted over a longer range. We know that the strong nuclear force is a contact force. It's a much shorter range, but it is strong enough to overcome other forces, which is why it's named the strong force. All right, I would like everybody to take a few minutes and try different things. You can move your Velcro pieces one side to the other and see what you can come up with as I walk around the classroom. And I want you to show examples of strong nuclear force and electromagnetism. See how they interact with each other and what must occur. Remember our rules that we've done. If it does not come in contact with each other, but you still feel a force, it would be electromagnetism. If two like charges are touching and yet they are not being repelled, we know that a strong nuclear force is being enacted. All right, let's take 5 minutes and I'll let you guys manipulate those things as I walk around.